An ideal blackbody. A large cavity that has a very small hole and is maintained at a temperature T is a good approximation to an ideal radiator or blackbody. Radiation can pass into or out of the cavity only through the hole. The cavity is perfect absorber since any radiation incident on the hole becomes trapped inside the cavity. Such a cavity at 400 degrees Celsius has a hole with area 4 millimeters square. How long does it take for the cavity to radiate 100 joules of energy through the hole? We can use Stefan's law. The emitted power is equal to Stefan's constant times surface area A, emissivity E times absolute temperature to the fourth power. Sigma, Stefan's constant, we know is 5.67 times 10 to the minus 8 watts per meter square Kelvin to the fourth power. The temperature given here is in degrees Celsius. We have to convert to absolute temperature, 400 plus 273, which is 673 Kelvin. Surface area is 4 millimeter square, that is 4 times 10 to minus 6 meters square. Emissivity for a black body is 1 because it emits all the radiation it absorbs. Now, power emitted means we are emitting a certain amount of energy in a unit time. So how long does it take? Delta T is equal to delta E divided by the power. So let's look at the energy we're emitting, 100 joules. The power is sigma, Stefan's constant, 5.67 10 to minus 8 watts per meter square, Kelvin to the fourth power, times the surface area, 4 times 10 to minus 6 meters square. Emissivity was 1, and we also have temperature, absolute temperature, 673 Kelvin to the fourth power. So this will give us a delta T of 2.15 times 10 to 3 seconds. Okay, so that's how long it takes to emit this much energy. Alright, so in this problem we have a direct application of Stefan's law for blackbody radiation. The emitted power is basically Stefan's constant, surface area, emissivity times T to the fourth power. For a large cavity that has a small hole maintained at a constant temperature T, the problem statement says radiation can pass into or out of the cavity only through the hole, and the cavity is a perfect absorber. Any incident radiation on the hole becomes trapped inside the cavity. So emissivity is basically equal to 1 for the black body. The absolute temperature has to be converted to Kelvin. So 400 degrees C is 673 Kelvin roughly, and the surface area is 4 times 10 to minus 6 meters square, because 1 meter is 1000 millimeter, and the power emitted is basically energy emitted per unit time. So the time is energy divided by power, so we can substitute the numbers and obtain 2.15 10 to 3 seconds.